Hi everyone, welcome back. In this section we're going to look at a new coordinate system called polar coordinates. As a bit of motivation, let's look at the coordinate system we're used to working in. This is known as the Cartesian coordinate system. You might not have been explicitly told the name of the coordinate system you've been working in all along, but it's the Cartesian coordinate system, also known as the rectangular coordinate system. And how does this coordinate system behave? Well, we want to define the position of a point. Okay, so positions are always measured relative to something that's fixed. In the Cartesian coordinate system, the thing that's fixed is a couple of axes. We fix two axes in space. One which we call the x-axis typically, and one which we call the y-axis. Now from these axes I can define, or describe, I should say, describe the position of any point. So if I have a point in space, I can describe it by its distance it is from the x-axis, that's going to be its y value, and the distance it is from the y-axis, that's going to be the x value. Using those two distances, I can describe the point with those two numbers, x and y. They're x and y coordinates. Given any point in space, I can describe its position relative to these axes, and that's the Cartesian coordinate system. So what would another coordinate system look like? Well, in any coordinate system, we need something that's fixed, a frame of reference, a place to measure things from. So in this coordinate system, we're going to fix a point, and that point's what we're going to call the pole. And we're going to fix a line segment. And this is going to be the polar axis. You can think of this polar axis as like the positive x-axis, and the pole is like the origin. Now, once we have the pole and the polar axes, I can describe the position of any point. How do I describe it? Well, I can assign to it, first of all, a number which gives its distance to the pole. That would not be enough to describe the position of this point because there's a whole circle of points around the pole whose distances r from the pole. Basically, any point on the circle of radius r would be distance r from the pole. So we can specify this point by how far around the circle it is. And to do that, we can use an angle theta. The angle theta measured from the polar axis to the line that connects the point we're interested in to the pole. And r theta in this case would be the polar coordinates of the point. R theta are the polar coordinates, as opposed to x, y, which are the Cartesian coordinates. So this is the polar coordinate system. The polar coordinate system, we're measuring a point, the position of a point, in terms of its distance to the pole and the angle that that line segment makes with the polar axes. So that, just to summarize all the terms we just introduced, they're included here below: pole, polar axes, and the like. And there's a little bit of information here about any point in the plane can be described in terms of values r and theta, where theta is between 0 and 2 pi. But we don't have to include 2 pi because any point that's on the polar axis also has an angle of 0. But this starts to indicate that, hey, wait a minute. If I did use an angle of 2 pi, I would get to the same point by using the angle theta being 0. The polar coordinate system has this property that points can be defined by different polar representations. Different r values and different theta values can give the same point. Whereas in the Cartesian coordinate system, the x and y coordinates are unique. You have a point, there's only one x value and one y value that can describe that point. But we're going to see that in the polar coordinate system, we can have multiple representations for the same point. So let's look at some examples of plotting points using polar coordinates. So in this first example, let's plot the point r equals 1, theta equals pi by 4. So typically we start with the theta value. That gives us a good indication of where it sits in the polar plane. So pi by 4. That means we're along this line segment here. How far along that line segment? We're 1 unit away from the pole. So that's 1 comma pi by 4. about this next point? 2 5 pi by 4. Well, I can think of 5 pi by 4 as pi plus pi by 4. So that's go around to pi, and then pi by 4 more. So I'm along this line segment. How far along? 2 units along. So maybe there's 1 unit and there's 2 units. So there's 2 5 pi by 4. How about this next one? 2 negative pi by 3. Oh, well, what's negative pi by 3? Well, if you notice in all the examples, we've been measuring angles. The positive way an angle moves is counterclockwise. So angles are measured counterclockwise from the polar axes. So what would a negative angle mean? Well, it would mean that we're measuring pi by 3 radians in the clockwise direction. So we would go pi by 3 units in the clockwise direction from the pole. And then 2 units along. So we're out here somewhere, so that's 2 negative pi by 3. So how about this last example? Negative 1, 5 pi by 6. So 5 pi by 6, we can think of that as pi minus pi by 6. So pi backing off a little bit to pi by 6. Oh, but then I run into an issue. What is negative 1? What is negative 1 units along there? I want to be of distance negative 1 from the pole. Okay, so here's where we think of it in the following way. Think of a real line. So the whole x-axis, if you want to think of it that way. You have positive values and you have negative values. And what we're doing here is we're essentially taking this whole line, the polar axes being the positive values, but then there's also these sort of negative values that are hanging on the end, and we're rotating. And if we rotate the whole thing to 5 pi by 6, then this turns out to be all those positive values on that real line. And then what's off the back end are all the negative values. So negative 1, 5 pi by 6, I go 5 pi by 6 radians out here. 1, let's point that, it might be worthwhile putting this down. 1 5 pi by 6, which we can certainly plot, would be here, but that's not what we want. We want negative 1 5 pi by 6. So negative 1 just means, oh, we're on the negative part of that real line, on the opposite side of the pole, 1 unit on the opposite side of the pole. So there would be negative 1 comma 5 pi by 6. So this is our convention for dealing with negative r values. They just mean we're on the opposite side of the pole as where we would be if the r value was positive. So let's look at a few more examples. 1 pi by 2. So let's plot these points. So pi by 2, we're at a right angle there. We're 1 unit along. So here we're up here somewhere. So there's 1 comma pi by 2. What about the next one? 1 5 pi by 2. 5 pi by 2. 5 pi by 2, what's that? That's 2 pi plus pi by 2. So that's a full revolution, 2 pi, plus another pi by 2. And then we're 1 unit along. Oh, we're at the exact same point as we were before. 1 5 pi by 2. So there's 2 different representations of that same point. This point in space, that point, it's the same point, it's just a point in space. We've managed to represent it in 2 different ways based on the angle. What about the next one? Negative 1 3 pi by 2. So 3 pi by 2 is down here. So that's 3 pi by 2. And our r value is negative 1. So that's telling us slingshot to the other side of the pole, 1 unit. Maybe 1 unit. So maybe I'll shade in what would be the value if the r value is positive. So this is sort of a shaded in dot. It's not really there, but this would be the 1 comma 3 pi by 2. Terrible shading on the dot. So let me just do it a little small one. So a little small dot. That's 1 3 pi by 2. But we don't want that. We want negative 1 3 pi by 2. So that means we want to be on the opposite side of the pole. That's the dot we want. That's the point we want. Negative 1 3 pi by 2. Oh, and would you look at that? It's the same point again. Here's 3 different representations of that same point. You can change the angle, or the r value could change as well. But if you start to think about this, there's really only 2 possible r values you can use to describe the position of a point. It's either going to be positive or negative, depending on your angle, of course. If your angle puts you to the opposite side of the pole, then you use a negative r value to get back to your point. If the angle puts you on the right side of the pole that your point's on, then you just use a positive r value. But there are multiple, infinitely many different theta values you can use depending on how many times you want to spin around the pole before you land on the angle that you want, or on the line segment that you want where your point is. Let's look at this next example. Plot the point given by polar coordinates 3 pi by 3. Then find two other pairs of polar coordinates of this point, one with the r value positive and one with the r value negative. So here we're going to come up with the multiple representations. 3 pi by 3. So pi by 3 is somewhere up here. We're 3 units along. So 1, 2, 3. So there's our polar coordinates. We want two other pairs. Well, one other pair I could easily get by, instead of going just up pi by 3, I'll go up pi by 3 and then another 2 pi around. So here's another representation. 3 and then pi by 3 plus 2 pi. So here we're writing down our alternate representations. So there's our first one. Pi by 3 plus 2 pi. So that's another way to write that would be just 3 and then 7 pi by 3. 3 and 7 pi by 3. What's another representation? Well, I could spin around many times as I want, but this one's telling me that I want one with an r value of being negative. So what I'm going to do is I'm going to take my angle, maybe I'll use a different color for this. I'm going to take my angle and land on this line there. So I want an angle that lands me on that line segment, because then I can slingshot my way to the other side of the pole by using a negative r value. So what's this angle? Well, it's pi by 3 plus another pi. So that's pi plus pi by 3. And what is that? That would be 4 pi by 3. And then I'd use a negative 3 as my r value to slingshot me to the other side of the pole. And so the other representation would be negative 3 pi by 3 plus pi, which is negative 3 and 4 pi by 3. So there's two other representations of our point. Again, in contrast with the Cartesian coordinate system, every point has a unique xy coordinate. In the polar coordinate system, we can have multiple representation, multiple ways to describe the point using r values and theta values. And now let's look at how we can go between polar coordinates and Cartesian coordinates. So let's see if we can convert from one to the other. So here we've got a point. And there's a couple of ways to describe it. We can use its Cartesian coordinates, so it's x, y values, or we could use its polar coordinates, its r and theta values. What's the connection between these? Well, let's draw our right triangle here. What's this distance? That's y. What's this distance? That's x. So what's the connection between these lengths, these side lengths of a right triangle, and the angle? Well, r cos theta is x. Or in other words, cos theta is side adjacent over the hypotenuse. Cos theta is x over r. I've just written it as r cos theta in this way. R sine theta, the connection between r sine of the angle is with the opposite side. So r sine theta is y. What are some other connections? Well, I can look at the connection between the angle and the height and the base of the triangle. That's the tangent. That's the relationship involving a tangent. So tan is y over x. What's a relationship disregarding the angle but just involving the sides? Well, this is a right triangle, so that would be the Pythagorean identity. R squared is x squared plus y squared. So here we've got a bunch of relationships all between the different quantities. How do we go then from polar to Cartesian? If I know the polar coordinates of the point, I know the r and the theta value, how do I get the x and the y values? Well, I look at my relationships and I say, hey, x is related to r and theta. X is r cos theta. So if I know the r and theta value, I can get x. Oh, and y is r sine theta. So if I know the r and theta value, I can get y. So there's our polar coordinate to Cartesian coordinate relationship. How about the other way? Cartesian to polar. if I know the Cartesian coordinates, how do I get the polar coordinates? If I know the x, y values, how do I get the r theta values? Well, if I know x and y, then this first one gives me a relationship between x, y, and theta. The second one gives me a relationship between x, y, and r. So those are the relationships I want. R squared is x squared plus y squared. Tan theta is y over x. So I can use each of these to determine what r and theta is. Now notice that there are two solutions to this first equation. If I know the x and y values, there are two solutions for r, a positive r and a negative r. And there are two solutions, or sorry, not two solutions, there are infinitely many solutions to this equation. Tan of theta equals y by x. Tan of theta equals y by x. Tan of theta is periodic. So whatever y by x is, there are infinitely many different theta values that I can choose. And this is connected to the idea that there are multiple representations of a point in the polar coordinate system. The r values could either be positive or negative, and the theta values could involve multiple trips around the pole, and those are represented here in terms of solving these equations. So you're not going to get unique values for r and theta, but you need to pick one. You need to pick a value of r and you need to pick a value of theta, which captures your point. So let's get some practice in doing these conversions. Let's convert the point 2 pi by 6 from polar to Cartesian. So in our polar coordinates, we're looking at 2 pi by 6, so it's somewhere down here, 1 unit, 2 units along, an angle of pi by 6. What is our Cartesian coordinates of this point? Well, we're going to use the conversion that x is r cos theta. What is r? That's 2. What is theta? That's pi by 6. Cos of pi by 6 is root 3 over 2, so x is root 3. What about the y value? R sine theta, that's 2 sine of pi by 6. Sine of pi by 6 is a half, so that's 2 times a half, or 1. So this is root 3, the y value is 1, so our Cartesian coordinates are root 3 and 1. So one thing you should notice here is that when I just write an ordered pair like root 3 comma 1 or 2 pi by 6, it's not clear just from that alone whether it's a Cartesian coordinates or the polar coordinates of the point. Before, we didn't have to clarify because we were only working in one coordinate system, the Cartesian coordinate system. But now we've got these two different coordinate systems. So when I write down an ordered pair, two numbers, we need to tell the person who's reading it, is that a Cartesian coordinate or is that a polar coordinate? And so you've got to read from the context of where it sits. In here, convert the point from polar. Okay, so that means that that thing is in polar coordinates. Here I've expressed it as Cartesian coordinates and then written the point down. So this tells you that the point I've written here is in Cartesian coordinates. Let's look at another example. Plot the point whose polar coordinates are 2 root 2 and 3 pi by 4. So 2 root 2, 3 pi by 4. 3 pi by 4 is right around here. That's 3 pi by 4. And we're 2 root 2 units along, so that distance there is 2 root 2. What are the Cartesian coordinates? Well, x is r, 2 root 2, times cosine of the angle, 3 pi by 4. Cos of 3 pi by 4, what is that? Well, the reference angle here is pi by 4. There's our reference angle. Maybe I'll draw it in red. There's our reference angle, pi by 4. Cos of pi by 4 is 1 over root 2. So cos of 3 pi by 4, because now we're in quadrant 2, that'll be negative 1 over root 2. So that's negative 1 over root 2, or negative 2. What's our y value? That's 2 root 2 sine of 3 pi by 4. Sine of 3 pi by 4, that's 1 over root 2 as well. And this time it's positive because it's sitting in quadrant 2, and the sine of an angle in quadrant 2 is positive. So that's 2. So this is negative 2 and 2, and these are the Cartesian coordinates. Negative 2 comma 2. You'll notice that in these examples, I'm sort of mixing the coordinate systems, right? I've got the points drawn in both represented in terms of the r value and the theta value, but I'm also overlaying the Cartesian coordinates in the same grid. And this is typical. We'll sometimes do this. We'll overlay the Cartesian coordinates and the polar coordinate systems on the same grid. It'll be clear which one we're referring to, because if I make notches up the x and y axes, those are referring to the Cartesian coordinates. But of course, if we're looking at the distance as well, I mean, a point sitting on the y-axis, the distance is just the corresponding y value. So it's natural to overlay these two coordinate systems on top of one another. Let's look at converting in the other direction now. Represent the point with Cartesian coordinates -1, 1 in terms of polar coordinates. So here we're looking at -1 and 1. There's our point. We want to represent it in terms of polar coordinates. That means I need to know the distance. What's my distance there? Well, r squared is equal to x squared plus y squared. So that's 1 squared plus 1 squared, or 2. So r is equal to √2. There's our distance. There's our r value. What about our theta value? Well, we have tan of theta is y over x. Y is 1, x is -1. So tan of theta is -1. There's multiple theta values that have tangent of -1. They live in either quadrant 2 or quadrant 4. I'm interested in terms of this diagram for the ones that sit in quadrant 2. And in particular, I probably want the first one, the smallest theta value that gets me into quadrant 2. How do I get that? Well, typically I would look at something like a reference angle here. What's this reference angle? Well, now I've got a little triangle whose height is 1 and whose base is 1. So I know that that angle there is pi by 4. So the angle I'm really interested in is this one here, which is pi minus pi by 4, or in other words, 3 pi by 4. So that's our angle, 3 pi by 4. And so our polar coordinates are √2 and 3 pi by 4. How about this next example? Cartesian coordinates are -2√3 and -2. So we're out here at -2√3 and down here at -2. So something like this. What's our corresponding r value? Well, r squared is x squared plus y squared. So that would be 2√3 squared. I'm going to drop the negative sign because I'm squaring it anyway, so it would become a positive number. Plus 2 squared. So that's 2√3 squared, that's 12. Plus 4, that's 16. So therefore, r is equal to 4. That distance there is 4. What's our theta value? Well, tan of theta is y over x. So -2 over -2√3, which is 1 over √3. And we're living in quadrant 3. So I want to know that reference angle there. Now we're staring at a triangle. Maybe we should draw this triangle. We're staring at a triangle. I want to find that reference angle out. So the triangle we're staring at looks like this. There's the angle I want to find. Let's call it alpha. This distance here is 2√3. This distance here is 2. We want to know what the angle is, alpha, such that tan of alpha is 1 over √3. Well, that angle would be pi by 6. That's our reference angle. That's pi by 6. Now we want to find this angle here. Well, that would be pi plus pi by 6. So this tells us that theta is pi plus pi by 6, or in other words, 7 pi by 6. So our polar coordinates are 4 and 7 pi by 6. So there's some examples of going back and forth between polar and Cartesian coordinates. One of the really important things that we're going to be using later on is the conversion from polar to Cartesian. And we're going to use it in somewhat of a surprising way. If we think about, well, okay, what we're going to do next is we're going to start to look at sketching curves given in polar coordinates. And we're going to start to use graphing utilities, the computer, software on the computer, to do these graphs for us. But sometimes a limitation with the software is that it doesn't recognize polar curves in the way we're going to describe them next. So if I fire in an equation in polar coordinates, it has a hard time graphing them. Instead, it would like equations in Cartesian coordinates. So we're going to convert our equations into parametric equations in Cartesian coordinates. We're going to use the stuff we just looked at in the last section. And how are we going to convert from polar to these Cartesian equations? We're going to use this connection here, that I can describe the x value by its r theta value. I can describe its y value by the corresponding polar r theta value. So these are going to be the really important conversions that we're going to use in a little bit. And I just wanted to point that out because we are going to use them in somewhat more complicated ways than what you might have seen here, where we're just converting between representations of given points. Okay, so let's end with a last example before we go on to curve sketching. Let's sketch this region in the plane consisting of the points who satisfy these inequalities. So the r values between 1 and 2, and the theta values between pi by 4 and 3 pi by 4. What do the set of all points that satisfy those things look like? I'm going to start with the theta values. Theta is allowed to go between pi by 4 and 3 pi by 4. So I'll sketch out theta is pi by 4, and I'll look at theta is 3 pi by 4. Our r value, our distance from the pole, is between 1 and 2. So we're out here. There's a circle, or portion of a circle of radius 1. There's a portion of a circle of radius 2. So I can indicate that here along the axis. That's 1, and that's a distance 2. And, maybe I could even specify this as those are corresponding to r values equals 2, and these points along this arc are corresponding to r values being 1. Now we're interested in all the points, r and theta, all the points with polar coordinates whose r value is between 1 and 2 and theta is between these ones. So that's all of these things here. All these things inside. But there's also a little bit more we have to consider. We're allowed to let r be 1. So our point is allowed to live on this arc. So I'm going to use a solid line to indicate that points on the arc are included. Much like for intervals, we use either solid dots at the ends or open dots at the ends to indicate whether the point at the end is in or not in the interval we're considering. There's a difference between open and closed intervals. Here we're using solid lines to indicate that points on it are in the set, whereas dotted lines indicate that it's not in the set. So I've left r equals 2 as a dotted line because r is not allowed to equal 2. How about our theta values? Which one should be solid and which one should be dotted? Well, theta is going to be allowed to be pi by 4. So I'm going to make that a solid line. But theta is not allowed to be 3 pi by 4, so that's a dotted one there. So there's our region of points that satisfy these inequalities. Okay, so next we're going to look at sketching curves given in terms of polar coordinates. And this is really cool because you're going to start to see some pretty interesting curves that we could sketch by hand using polar coordinates. And it's really neat to see this stuff.